Hi everyone. Welcome to our third talk of the series. So for those who didn't join our previous talks, the purpose of this talk series is to investigate the applications of machine learning techniques in astronomy. So we will invite speakers from different subfields of astronomy, but I think the same thing is that they will all talk about how they apply the machine learning techniques in their research. So today our speaker is JiaYu from National Central University. So JiaYu is currently a PhD candidate. So I just talked to him and realized that he's going to defend his thesis next week. So I really appreciate your time in giving the talk, especially at this moment. So maybe this is a great opportunity to rehearse your thesis defense. Yeah, okay. So JiaYu is expert in variable stars. So he has been published papers in using machine learning techniques in studying the variable stars. So the title of his talk today is the machine learning classification of Mira variables in magnetic clouds and M33. Let's welcome him.
Okay, so just like this topic, my share with the machine learning classification of the Mira variables and the magnetic cloud and M33. So we can move on to the next set. Yeah, here's my outliers. So first, I will introduction to the machine learning, and secondly, to share my paper, my first shares published paper, and third is the second published paper, and fourth is my summary. So yeah, next. So first, the machine learning is the AI technique. So it's very easy to classify something and maybe go register, or maybe you can clustering something. So you can use this machine learning technique to do the easily way to do the maybe 1,000 or 10,000 million data to classify into some type. And machine learning can easily be the supervising learning and unsupervised learning and something. So we next to the supervised learning. Next. So the supervising learning just like if I can classify which one is which one. So just like we have the oxygen type, or maybe have the carbon type. If we can get his label first, we can use this data to classify the unknown data. So they have a lot of the algorithm, just like the design tree, render forest, support vector machine, and linear regressions. So supervising is just like if we give the label first, and we can use this machine learning to get the unknown type. And next, the unsupervising learning, just like if we don't know which one is which one, just like we have the two in this data, we have the two groups of that, but we don't know which one is which one. But we can use the machine learning to cluster his type into the two groups, and we can use these two groups to differentiate that, to check his feature. And next, I need to introduce my use the machine learning algorithm. Is next. So my first use the algorithm is a perception learning algorithm. It's just like the linear separable. So it's just like the right hand side, we can see we have the two groups of the data. So we use the simple ones line to cut this group, two group things into the two cluster. So the perception learning algorithm just like a normal linearized separable. It's a single linear. And the next is the linear regression analysis. It's just similar like the perception. It just uses one line to cut the whole data into the two groups, but it's different in his affection function. So it's just similar to the perception, but it's different. And the linear regression analysis, his good is it can predict his possibility into the which one. Maybe his the first type is 90% possibility and 10% the possibility, but the perception he cannot give the possibility. So next, and next we use the nearest neighborhood. It's just like we have the square group in the left hand side, and we have a star group in the right hand side, and we can see the triangle. The nearest triangle is the star, so we can make the triangle's data into the star type. So we can use the distance to get which type, what is it. Next. Next. And next is the support vector machine. It's just like we have the 2D data and it will project to the more highly, maybe 3D, 4D use his feature. So he can find the hyperplane to cut in the more higher space. And when he cut the hyperplane, he will transfer into an original feature space. Yeah, next. And next is a random forest algorithm. So the random forest algorithm is combines a lot of the decision tree. So right hand side is the example of the decision tree. So it's just like if we input a lot of the feature into our algorithm, and it will use this feature to divide in the start divide into the two group and keep keep splitting keep keep delay keep that keeps the splitting in the two group, and it's keep go step by step. When all the leaves have the one classification, it is the final end. So if we combine the whole decision tree into the climate of that is the random forest. And the random forest can avoid the overfit the decision tree is one overfit. So that can easily and is useful and is a powerful machine learning technique. Yeah, so next. So if we want to know how powerful and how useful with the machine learning techniques, we can easily to use the two things to know is it good or not good. So we can use the receiver operation collections, just a ROC, just a right hand side. So use the ROC curve if we can know if the area under the ROC curve, if the value is 1 is the perfect performance, but it is the 0.5 is the random guess. And the right hand side, we also can use the confusion metric to know his true rate or false rate to know it's good or not good. Yeah, next. So if you want to know more detailedly and how to use the Python language to use, so you can see the Skillent website. They have a lot of the example, and they have the theme, and they have the useful, and any aggression you can just explain. So next we move on to the first journal. So I first study is the comparison study of the photometric prototypes between the regular and non-regular Mira in the marginal cloud. So next. So we need to introduction first for the Mira variables. And we can know the Mira variables is a long period variable. His variable time is from 100 to the 1,000 days. And he is very cold. The radii is effective temperature is around 3,000 K, and his radii is from the hundreds of radii. And it just like the normal RGB stars, so you can also divide into the arsenal rich and the carbon rich with his CO ratio in his atmosphere and net. And we not only use the spectra to divide his oxygen and carbon, so we also you can use the color diagram to make sure what his type in this Miras. And also next, and in marginal cloud Mira, we can see these two list like curve. So right hand side is the normal Mira, it's just like a regular Mira. He have the 1% periodic. We can see his like curve is very lightful. And the right hand side is a non-regular Mira. This is not only the setting periodic, it also have some long-term trade or multi-periodic. It shows not simply one periodic performance. And next, so we collide the Mira variable star in the OGO group with OGO 3, and we collide the 1,600 the Mira in the LNC, and we have the 352 in the SNT. So we also collide the JHK with the 2MAX and the large metrical near infrared dynamic survey with LNC star. And next. So just we cannot easily to classify the almost 2,000 line curve. So we use the random forest to classify this light curve into the regular and the non-regular. So we can not easily to just direct classify with his light curve. So we need to let this light curve into some value, some number to it can input into the machine learning. And this step in deep learning is just like it's called like the tensor. So you can input this to number. So I use the feature analysis for the time series. Use this package to let my light curve into the 12 light curve feature, and use this light curve feature input the random Fourier algorithm, and you can use this algorithm to classify that. So I pick the 100 regular and 150 non-regular light curve to divide that and input the algorithm, and use this training data to classify our final results. And I set the training process with the 5,000 decision tree, and each tree has the number of the 50 leaves. Next. So we can see the left hand side is my RC curve. We can see the area under the RC curve is 0.94, is quite highly value in that. So more close to the one is perfect performance. So the 0.94 is also very good. So, and also with the confusing matrix, so you can see the more the true rate is always above to the 90s, over the 90s, so it's very good. And finally, we can divide into the 694 regular Mira and the 1321 non-regular Miras. Next, we move on to the regular Mira. Next. So when we divide into a regular and a non-regular, we use the Longskagel periodic to calculate his periodics. And when we get his true periodic, after that we cut with his periodic into the one cycle to each pulsating cycle, and use that we can fit his light curve function, and use the light curve function we can get his magnitude of the maximum line and the mean magnitude of and the magnitude of the minimum. And next, so we we compare the whole. We get the magnitude of the maxima and mean line and the minimum line time. So we can see the minimum line time is consistent with the mean line time, and the maximum the standard deviation of the mean maxima is larger than the maximum line time. So we can use this result to know the maximum line time is most stable in the we compare with the mean line time. Next, yeah. Not only the maximum line time is so we can see the maximum line time is most stable, but the minimum lifetime have some trend. We can see it's just like maybe it's not periodic, and they have some periodic show, and they have a long-term trend show. So we can use this phenomenon to divide into three groups. Is no periodic, the periodic is from the 3,300 to the 3,000 days, and more than 3,000 days. And next. And after that, so we can use this this lifetime to magnitude to get his PL relation with LNC. So we use the two model to fit our PL relation. One is the two-slope model, and another is a quadratic model. Next. And we also combine the LNC and the SNC into one and use this general data set to fit the PL relation. Next. So in this, we can see the Arsenal ridge is a standard deviation of the region in the Arsenal ridge. We can see the maximum light is value is smaller with the mean light. It means the oxygen, the magnitude of the oxygen in the purification have the small dispersion in purification fitting. So if it is more smaller dispersion, we can use this to easily to fit the purification and calculate the distant merge rate. And next we can move on to the non-regular Mira next. So we fit the Likert function with two terms. One is a short periodic term, and another is a long-term periodic. So the dashed line is a long-term periodic Likert function, and we remove that is next slide. Yeah, so we remove the long-term part. We can see the remove the Likert is just like the regular Mira or the simple one. So next. And yeah, so we compare the short-term periodic and the long-term periodic. They didn't present any correlation in these two periodic. Next. Yeah, so we can also put the short-term periodic into the PL relation. It's not have the linear line into that. And next. But if we remove the long-term part, we can see the ascending ridge. The data of the ascending ridge will close to the PL relation function, just our fitting, no matter into the maximum lifetime and mean lifetime. But the carbon ridge, when it removes the long-term part, it didn't change anything. But the ascending ridge remove the long-term part, it will close into the PL relation function. Next. So we compare to the regular and the non-regular Mira difference. So next. So we fit is we use we collect the photometric data with the simple database to fit his SED machine, SED fitting. So we use the two black body radiation function to present the start part and the dust component. So just like we have the 2D disk model. And the start part we have the black body temperature is between the 2000 K and the 4000 K. But the dust component is from the 10K to the 1800K. Next. Yeah. So that is our photometric data list. Next. Next. Yeah. So we fit the two part of that. So we can see the right dashed line is the start part SED function, and the blue dashed line is the dust component. So in our 2D disk model, we can see it can easily to fit the SED with our photometric data. Next. So the left hand side is the regular Mira, the SED fitting. The right hand side is a non-regular Mira SED fitting. So we can use this directly use the SED fitting to, we can see is very different into these two groups. The non-regular Mira has a more stronger dust component to, yeah. And but in the regular Mira, the dust component is not so much. The next, so we combine this whole regular Mira and non-regular Mira SED to compare to that. So we can see the regular Mira has simply clearly the peak into the 1 micron, but the non-regular Mira is from the 1 micron to the 10 micron, have the peak is not into the 1 here. And next, and we also compare his color vector. So we can see the time series color variation. The left hand side is a regular Mira. We can see the button figure of the left hand side. We can see when the light mechanism is go on, the color is go blue, but the color is the mechanism is go darker, but the color is go red. So it's just like normally pulsating variable. When he goes, the temperature go on, the brightness go on, and he's bluer. The mechanism is go down, and it's more redly. But in the non-regular Mira, is right hand side. The general light curve is go down, so we can see the general light curve is go darker, more fainter, but his color is more bluer. When his brightness go bright, and his color is go red. It's a very different way between with the regular Mira, and this phenomenon is just present in the young stellar aperture. This effect is called the blue effect. Yeah, next. So we can collide the complete the Mira in the LNC. We can see the regular Mira his magnitude O is brightened with the 17 I magnitude, but the non-regular Mira will go more fainter, more darkening. And next. So next, we move on to the fundamental investigation of the M33 Mira in the distance scale application. Next. So we combine the photometric data with several surveys, and we pick the sample of the Mira in ancestry to come from the event catalog, and we also collect his JHK catalog, and we line the GRI band in the CFHT and the GRI band with the pen stars. And we also collect the PDF and IPDO data in R band. And we use the pen star catalog to use this differential photometry for transfer the R big R into the small R band. And we also collect the GRI band with the ZTF data until the 2021. So the whole life curve span into the 18 years. And next is the photometric data example with our light curve in the M33. So the left we can see we from the 2005 and to the 2021. And next. And we combine this light curve, so we also can to determine his periodic with multi-band long gargle and multi-band phase dispersion minimization per mass. And when we get the periodic, we can see the right hand side figure, the top, you can see the blue light is our multi-band loss gargle get the periodic, and the middle panel is do the periodic with the multi-band PDN. And next, when we get the true periodics, we fit the light curve function with in the phase space. So just like the bottom of the right hand side. So we fit the I band, R band, G band with like a function and get his maximum magnitude and mean line magnitude and also the minimum light. Next. Yeah, so when we get the magnitude of a GRI, we also compare with in his near infrared data. So we can see the periodic with the color in near infrared to the optical band. It's easily can see in the J minus case group, the oxygen and the carbon is a different group, and the H minus case is a little bit mixed, and in I minus H, whole carbon rich and oxygen rich is mixing into one group, and we can see if we only have periodic and the J minus K, we can easily to divide it is oxygen or carbon rich. And next, so we climb the LNC. The right hand side we can see the LNC oscillator is can easily below under the around the 1 color J minus K, and the carbon rate is above is over the 1 or J minus K, and we can see the N33 is also have this these things. Yeah. So we use the PLA, RLA, and the KN in the supervac machine. Use our LNC and the N33 data, so we classify unknown data in N33. So here is the confusion matrix with the PLA and the RLA. The next is the confusion matrix with the KN and the supervac machine. So we can see the most higher true rate is his possibility is use the KN is the best the algorithm in our text. So we use the KN algorithm to our machine learning work to classify the unknown type Mira in the N33. Next, and here is the result of the machine learning data. So we use the KN classifier to can divide into the 301 oxygen rich Mira and 34 carbon rich Miras with periodic with J minus K next. So when we classify, after we get classified, we combine the whole ancestry oxygen rich Mira. We feed the pure ration in the maximum light with the projected model. So we can see the ratio, the standard deviation of the residual is was 0.42. And next, the mean line is the standard deviation residual of the residual was 0.57. So in Ancestry, it also can present the oxygen-rich Mira has the small dispersion in the pure ration. The maximum line is smaller than the mean line time. And next, so we also change our small I band transfer into the big I. So we use the transfer function and use the GR color magnitude, let our small I band into the big I, and we also use our result in the LNC oxygen-rich relation function to get our ancestry distance. So we can get the distance measured is 24.67 magnitude at the maximum light. And next, so we can see our distance measured compared to the previous lateral measure. So we can see our result is very consistent in another journal, another papers. So we think the maximum light time to use into the purification is good in good math is a new math to determine the distance of the Mira. And next is our summary. So our summary can see the regular shows the stable magnet in the maximum light time. So, and also the non-regular have the displays is correlation with his the periodic magnitude and also the long-term variation didn't have any correlation with his periodic and the dust. And we can use the machine learning technique to divide the oxygen rich and the carbon rich to reclassify the unknown type Mira with the periodic and the J minus K. And also the oxygen Mira has the maximum lifetime in the oxygen Mira's population has the small dispersion with the mean lifetime. And we find the distance measure is from the 24.67 in magnitude with the maximum lifetime. So that is new way to measure the P relation, get the distance moderate. So maybe we start here.
Okay, great. Any questions for JiaYu? So you can either raise your hand, okay, or type the questions in the chat box. I can see the Edward. Can you speak?
Hello.
Okay.
So I have a question about how you select your training set.
Yeah, so we have two groups. We have two machine learning work. So in the first, the classify the regular and the non-regular. It's just like we direct use the light curve by the human eye. So we collide the step by step because that is new classified. So I use the human eye to case by case to select the 250 sample to the training data. That is not so much, but it also can use into the classify into the regular and the non-regular. And the second is we class the acceleration and cooperation. It's just original has classified that. So I direct use the ancestry class already know the acceleration and cooperation. Use this tool to into the training set.
Okay. We have one more questions. Okay, please speak up.
Hi, JiaYu. Thank you for the sharing your research topic with us. So I have two questions. One is, in the case of your training data, how long do you have the training data? I mean, with respect to time, I mean days or years or how long? And the second question is, what should be the key takeaways from your current research work?
The key of
Yeah, key takeaways. I mean, if you would like to summarize your whole work into few sentences other than the summary that you're presenting here, what should be the key takeaways for the audiences?
okay. The first part is not so large because the data set is not so big. It's maybe just training with 1 hour is 10 minutes or something. It's not so much. And the second part we can get it's just like the original we classify with Mira with his spectra, and he can easily use maybe the spectra. We can see the carbon to the oxygen ratio. This normal thing to classify is oxygen rich and carbon rich, and also can use the color diagram is J minus K and V minus I with the algorithm. So we use the periodic and with the J minus K is not original math to classify the acceleration and the carbon ridge. It is not a new way, but it's proves this. Just use the periodic and the near-infrared data can use classify the type of that, and also we also can use the maximum line time to get the distant measure rate. That is a new text and new result in the past. So yeah, so we can in this talk we can see we can use the machine learning technique to divide the different class, different type of Mira is useful. Yeah.
Okay, thank you for your answer.
Thank you. Any more questions? Edward? Yeah, please.
Yeah, can you talk more about your like feature? So you put the feature into random forest, right? Can you talk about those features?
Yeah, I use the feature of the time series. The display package we input the like of function, the like data into this package. We can get a lot of the feature. So we use this package to calculate just like this amplitude beyond one standard deviation, car sigma, car tau, and the linear train. These 12 features is use this 12 feature into the random forest algorithm. So yeah, the whole feature, and we can see this whole feature importance in our random forest algorithm.
So what is the beyond one sigma and the car? What is the car?
That's the beyond one sigma, just like the not the Q1. It's how to say that? It's a cut of the Q1, just like the 25% to get his standard deviation. And the car and the tau is just like a normal sigma and tau, but it will just like the bootstrap will take something out, and the right and the calculate is sigma and the general normal, like the how to say that. Yeah, it's with some math calculator with whole like of the dispersion. So yeah, if want to more detail, can see the website or the paper with the can see the feature of the time series. This package have the one paper, so I have the more detailed. Yeah.
Okay, more questions? So can you say a little bit more about like how you choose which machine learning methods to use? For example, the first part of your results, you apply the random forest to distinguish the regular and non-regular Miras. And for the second part, I think you use the KN, or you just use many methods you just not mentioned here.
Yeah. So in the first, we cannot easily to get it originally has a like of feature, like function, like data. So if we get the like data, is not only It's not easy to into the 2D or 3D specs into the to classify, because the light curve is just like the normal the function, just like the pulsating light curve. So it's quite like things like the, if we can detect with the profile, we use this profile to get the classified, but we need to transfer this light curve into the numbers. So if we just use the one or two feature, it cannot easily to divide into the classified. So we have the 12 features. So in this so much feature into the algorithm, so it's not easily to use in the PA, just like the percentage or linear register logic. Sludges register is just like they have simply 2D data, and you can use simple line to cut into a two group. So in first part, we need to classify the light curve. So it's more complex with the feature. So in the first part, we directly use a random forest because it's not easily can divide into the 2D group dataset. We have the 12 feature into that, so we use useful, and we can input more feature into the training data. So we choose the random forest into first part, and the second part is just the periodic with the color. We want to more simply classify, because the normal is a J minus K and V minus R. They have a 4 term. So we want to get the periodic and with J minus K. It's just a 2D space. So in this data set, it's just 2D space. It is easily can use the perception and large logistic and KNN or small vacuum machine. It easily can use that into the 2D data set. So we use this 4 algorithm to text and choose one. And yeah, you can use the KNN and the support vacuum machine in the more feature space. That is just is useful, but it's in the 2D, so we can easily to use to classify that. So that's why I chose.
Okay, thank you very much. That's clear. Any more questions before we finish? Edward, please.
Yeah, sorry, I found this interesting. I have many questions.
Yeah, no problem. Yeah.
So the question is, so before your work, before this machine learning to find the regular and non-regular Mira, how people do to separate them?
No. Regular and non-regular is my classified. In the past, the just like the Mira, and the Mira has a long-term trend, but they don't have any classify or any type, any paper to divide into the two groups to discussion that. So I use my class to into a regular and non-regular. In the past, they didn't have so much. They only have the Mira with long-term trade.
So a following question. So they say it's Mira with long-term trend. So it sounds to me that they somehow put it into FFT, do the Fourier transfer, and then if they have some long-term frequency, it's Mira with long-term train. Is that correct?
The Mira didn't have a long-term train.
And sorry, you say they separate the Mira to Mira and the Mira with long-term trend, right?
How to say that? And in the past, the Mira only not only just like it will classify, it not classify. They calculate the Mira with his light curve, and if they have something more long turning or they have some training, they just say, oh, this Mira has some long term chain. So it's not lexic. They only just like they have the phenomena, they have the preset, they have the small, they have the some long term, the trend or long term exchange with the time. So how to say that? Normally, just directly calculate his short-term periodic and no discussion with his long-term. Maybe just like the white clock in the 1997 and 2004, he just he just calculate his periodic and say that maybe have the 2000 days long term or the 10,000 days long term. He just say that he calculate that maybe have some long term, so you don't have any classify of that. But in some AGB star they have the long second periodic very variable. It's not. It is different. His long second. His second periodic is more long term, but his amplitude is very small. So this is the difference in the previous work. Yeah. So that's your question.
Okay.
Yeah. Thank you.
That's an interesting question. Any more questions? Maybe. Oh, okay. We have one more question from Shen Yuan.
Thanks for the nice talk. Just follow up that a little bit. I'm curious. You mentioned one of the most important results is to use Mira for the distance module, and you listed the literature works, and many of them are done with Cepheids. So I'm just curious whether you have any. Is there any advantage of using Mira?
Can you say that again?
So in your result, you mentioned that you can use Mira for measuring the distance, right, to derive the distance module, and you compared your results to earlier works. And in that list, many of the works are done with different methods, like using Cepheids. And so I'm just curious, this particular approach you take, is there any advantage with this particular approach you are using?
In the normal distant moderate mesh is maybe just like the mean light periodization or TRGB or TAGB. So in our work, we just want to use the maximum like time to get the distant moderate. Just like if we can see the more detail, or just like we can only detect the maximum light, not the whole light curve. If we can get the maximum light and his periodics, and we can just use not collide the whole light curve, and we can just use the maximum light and his periodics, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light curve, and we can just use not collide the whole light we can just use this maximum line to calculate the distance measured with the incomplete data set. So that's as I know, it's the first time use the maximum line time to get the distance measured with the Mira. Yeah, this is the first time test.
Okay, thank you.
Great. So if there are no more questions, thanks, JiaYu, for your time. Yes, I know you're going to have defense next week, and yeah, it's great to have you here. So I think our next talk of the series will be held on September. So if you're interested, please register. I think we will advertise when it's closer. Okay. Yeah, thanks again for joining. I'll see you next time. Bye.